Sounds like the mic's now on. The title of my talk is Building a Data-Friendly Platform for a Data-Driven Future. But the talk's generally going to be about microservices, containers, big data analytics, and what's the best way to run these in our data centers and clouds. Which is what we're doing at Mesasphere. That's what we're doing at Mesasphere. A little bit about myself. I'm the co-founder and chief architect of Mesasphere. I was formerly at Twitter and UC Berkeley. And at UC Berkeley, I was a co-creator of a project called Mesos, which we put into the Apache Foundation in about 2010. And you can find me at Twitter at @BenH. So I kind of wanted to start by just giving my perspective, of really Mesasphere's perspective, of some reinforcing trends that we're really seeing in the industry. Really, there's two big ones that are really happening right now. One is microservices, and the other one is containerization. So when I used to give a presentation that was something like this, I used to put the word micro in parenthetical comments and just kind of say services, because the transition from sort of service-oriented architecture to microservices is in some ways a minute one. But just there's this resurgence of people thinking about building their applications by breaking it down into a bunch of these service components again. And I think what's really interesting is that these two things are driving a lot of organizations to realize and decide that they need something like container or cluster or resource management. And so I'm going to talk a little bit about how we actually do that. Now, the way I really see the reinforcing trends is looking something a bit more like this, where there's a bunch of organizations that are kind of getting on this circle at different parts, and that's reinforcing them to actually do all the things. So there's a bunch of organizations that are starting to do containerization that are not actually doing microservices, and that's kind of driving them to do things like cluster management, resource management. There are organizations that are starting to do microservices that are not doing containerization, and that's driving them to do things like container and cluster resource management. There's even some organizations that are just starting to use cluster managers for their existing applications. They're not bringing them into microservices. They're not doing containerization. There's another category here as well, which is there's organizations that are trying to do big data and analytics, and they're trying to figure out the best way to do this. And for a lot of those organizations, that is driving them to build something that looks like microservice architectures. For a lot of them, it's causing them to stick their software into containers. And many of them, it's driving them to use things like resource managers to make it more efficient to actually run their big data and analytics. So a little story, a little background to kind of motivate all this. When I was at Twitter in early 2010, Twitter was not a microservices-based shop. Twitter got on that sort of circle by doing really cluster management, resource management, and microservices, not really containerization the way we think of containerization today. So Twitter was actually a giant monolithic Ruby on Rails application that we actually called the monorail, which I thought was a really cute name. And it pretty much did everything. Giant Rails application got deployed across thousands of machines, everything except really storage. And in 2010, what we did at Twitter was we decomposed that giant monolithic application into a bunch of microservices. This is just a collection of some of those services. There was hundreds, if not thousands, by the time that I left the company. I think, again, what's really interesting is when we first started doing this, when we were presenting it to the community, we never said that Twitter was doing microservices. We actually said that Twitter was doing software-oriented architecture, and Twitter was doing SOA. And eventually, everyone in the community just said, no, you're doing microservices. So, where did this microservices thing really come from? And why were we doing it at Twitter? Well, I kind of stole the theme of this slide. This is not exactly a stolen slide. I recreated the slide myself from Adrian Cockcroft, who at Netflix was really behind pushing this idea of microservices. And the way he captures it, which I like to capture here because we were suffering from the same things at Twitter, is this idea of the pain of actually having to deploy and work in a monolithic architecture. And really, this is what happens. You've got a bunch of developers that are working on the same monolithic application. And when you go into QA to get your application released, if there's a bug that one developer had introduced, it holds up the entire deployment. It holds up the entire application from being deployed. And you got to go back to that single developer team and say, hey, you got to fix this before we actually deploy it. And this can be even worse if, for example, you deploy it into production and then you find the bug. You still have to roll back all the new features to a previous version, just so that one team, in this case, it was the team at the top for QA, and it was the team at the bottom for after release, that actually has to fix this. And so the pain of this is really, really felt by the entire engineering organization. And instead, rather than doing something like this in this very monolithic way, what Adrian Cockcroft really proposed, and what we embraced at Twitter, was this idea that each of the individual developers or development teams would have their own components, their own services that they would effectively deploy independently. And so, they'd be able to say, hey, I'm working on my deploy. It's at my own schedule. If we have bugs, we're going to fix our own bugs, and then we're going to redeploy. Now, it requires a lot more diligence when it comes to different parts of the infrastructure communicating with different services, but there's still a lot of wins. Okay? So this is really what we transitioned to at Twitter. And this is really a trend that I'm seeing quite a bit more in the industry today. A lot more organizations are moving to something like microservices. Again, not everybody. There's a lot of people that are just doing containerization, and they're literally containerizing their entire LAMP stacks. So they have these giant containers, which they're then running in their clouds or data centers. But a lot of organizations are moving to microservices. And they're really embracing these ideas of, do one thing and do it well, which is really the Unix philosophy. Compose the pieces together. Again, in some cases that can be more difficult as the actual iterations of the microservices are changing. But for the most part, organizations don't find it too difficult. And it has these nice properties of being able to test and debug the services in isolation. And it really nicely captures the organizational structure of independent teams working on independent timelines, trying to just ship their features. So there's one more slide I really have on microservices, just because I think it's such an interesting trend in the industry. This is, again, really just capturing, on the left-hand side, the monolithic stack and the way that we were deploying things to on the right-hand side, the microservices approach. And one of the things, beyond just independent teams actually deploying their software, that we found really, really valuable at Twitter was the ability to actually independently scale the services as well. So what that meant in the past is that if we had one function that we wanted more compute power on when it was in the monolith, we had to deploy the entire monolith, which could take up and waste a lot of resources. When you had just a microservice that you wanted thousands of, but it only needed one CPU and 1 gig of RAM, you could just deploy that single microservice that needed that 1 gig and 1 core across the entire cluster and really save a ton of resources. So you could have this dynamic sizing for each of the individual microservices. Okay, so microservices, again, in that wheel was one part of it. Containerization was another part of it. So I'm going to assume that a handful of folks are pretty familiar with containerization, and just kind of give my quick spiel about where I see containerization really fitting in here. Especially because at Twitter, we were not doing containerization the way that most of you are probably thinking about containerization, which is Docker container images. Containerization to us at Twitter meant, how are we going to package up our bits together with the dependencies that we might need so that we could run them as an independent unit. So if we had these small microservice deployable units, then we needed all the dependencies so we could run them somewhere in the data center. And historically, people have effectively done packaging or containerization lots of different ways. RPM, Git, run a Git command to pull down your bits before you actually would run it on the machine. If you're in the JVM land, using things like jar, tarballs, static binaries. It's my favorite one, actually. I think that's a very effective means of packaging up all the bits that you need. There's a reason why Go initially only built static binaries. It was because at Google, that's how they had to actually deploy the Go binaries. And then Docker really came around, and Docker was like, hey, here's another great way of actually packaging up your applications. You can containerize it, and you can stick the file system you effectively need in a container image. And really what I think, to me, is capturing this then versus now is there was a lot more moving parts in the RPM days, and there's a lot less moving parts in where we are today. And that determinism that you get from a lot less moving parts is something that really saves a bunch of organizations in the long run. And what I mean by that determinism there is here, the kinds of bugs in the RPM world that we'd run into is, for whatever reason, the kernel got upgraded, and now it was pointing to a slightly different RPM server, and so we were pulling down a dependency, which was a slightly different version of the dependency, which actually we were expecting the buggy behavior of the not previously upgraded RPM release. And so you'd run into these really weird kinds of bugs that you'd have to track down, and then you're like, you know what, I just want the version of the library that I know I did all my testing with to exist with my application. And the best way to do that is to package that up into a single container image. And so there's less moving parts as we actually moved to the Docker world. And then Rocket is another, so specifically AppC is another containerization format that's becoming really popular. So I like to throw VMware in here. Because there's a lot of people that will actually come talk to me and say, I use VMware for that way too. I use virtual machines to package up my application. I got all the dependencies I needed, and I knew I wouldn't have to install anything else and put them in my virtual machine, and then my virtual machine was my deployable unit. So why can't I keep just doing that? And my answer is kind of, well, you can. It's a bigger version of a container image because it has the entire operating system as well. But the fundamentals are actually the same. And really what people that were doing that with VMware, what they got when they moved to things like Docker was ridiculously fast snapshots. Because people that had that model with VMs, if they wanted to kind of package up all their dependencies in a VM and then ship it, it was a really painful process. They'd download their things, and they'd be like, OK, now my VM's ready. I want a snapshot of that version. Click a button, and then 5 minutes later, they actually have their VM. Whereas with Docker, they download their things into their image. They'd hit a button, and it'd have their snapshot immediately, and they could actually go and deploy it. But it's very fascinating to see all the research, a lot of which came out of academia, of doing things like deduplication of VMs, so you could really efficiently move VMs across the data center to get them scheduled in all sorts of places, and what we sort of have out of the box with things like Docker, just because it was a second generation of thinking about how we could actually package up our applications. So VMs, yeah, still interesting there. OK, so and then this last part that I mentioned was really big data and analytics, because, and this is kind of where the demo is going to go in the presentation too, is at the end of the day, microservices and containers is really not enough. Building some stateless applications, sticking them in microservices is really not enough for what most organizations need to do today. They need to also do some kind of data processing, to do some kind of data storage. And there's a lot of different distributed systems that are being built that are helping people do this. I've captured a couple here: Spark, Cassandra, Kafka, things like HDFS, Ceph. There's a whole bunch of these different systems that are being built, which are still cornerstone pieces of the infrastructure that we need beyond just microservices and containers. And what becomes really interesting is when you think about how organizations are actually going to run all these things, if they've decided they're going to move to microservices or not, if they're going to use containers or not, if they're going to be using big data processing, data storage, whatever it is, there becomes to be this big question of how do I actually run all these things? If this is my future application, it's all these components, how do I most efficiently and effectively deploy and operate all these things? It's a bunch of things in the data center today. And that's where really this rise of a new infrastructure, or this need for things like resource management and cluster management, has really kind of become a trend in the industry. And the big challenges that we really needed to address at Twitter, but I would say even before that when I was at Berkeley, the things that we were really thinking about were how do people do things like deployment and scheduling for fault tolerance? At Twitter, when you moved from a single monolithic application, which you were deploying on thousands of machines, to hundreds, if not thousands of applications that you needed to deploy across all these machines, what's the best way to decide which machines to run each of these different applications on? And I kid you not, in the early days, there was a spreadsheet where the rows represented racks and the columns represented the machines in the racks. And we'd be like, OK, I guess that machine will run this service, and this machine will run this service, and this other machine will run this service. And there were humans that were manually deciding how they were going to actually schedule these applications. And they'd say things like, oh, well, for this service, I want some kind of fault tolerance, so I'll run it across some of the racks. For this other service, I want to make sure that I have, it needs to be on the same rack because they're communicating, and I don't want to deal with going through the top of rack switch for latency issues. And so, this was a really real challenge. So I kind of mentioned some of this here as well, but another challenge was scheduling for being elastic and being as efficient as possible. This included if we ever wanted to be dynamic and launch more, be elastic and launch more applications. Like, how do you do that in a spreadsheet? It's just nuts. How do you do that like on demand? It's just nuts. This is not something you really want to take on. What's the best way to do things like service discovery and networking? When you move to a world where you don't have like one service, but you have hundreds of services, how are the services going to actually communicate? How are they going to find each other? How are you going to make sure that the infrastructure is dynamically updated so they can communicate with one another? And then, once it's all running, how do you do operations? How do you then go do maintenance of the data center? I guess now you've got this spreadsheet, and you can go and you can be like, well, I'm going to bring down the top of rack switch on this rack, so I'll go to each of the teams that have something deployed on this thing and tell them, by the way, you're going to have some of this downtime. How do you do upgrades? How do you actually have people upgrade their own software? So I sometimes in my presentations like to pull in some real emails from Twitter that actually happened. And I've scrubbed the names for the most part. Abdur was actually my boss. He was the chief scientist at the time at Twitter. So that name's real. But this says, hey, this box had to be rebooted. Were there any production services running on this machine? This is before the spreadsheet. Yeah, this is why the spreadsheet existed, right? And like, this is pretty nuts, right? So this is like wow, okay, I guess we need a spreadsheet so we can think about how to think about the failures and do that. And then here was the second one. There was maintenance, which is we were thinking about deploying some other things, and like, hey, we're setting up a couple of things. We'd like to know what rack switch and PDU these devices are on. Preferably they are on different rack switches and power feeds so that they're fully redundant, right? Like, this was the kind of manual scheduling that organizations were doing, and some of this happens in the cloud as well. This is not just an on-prem specific problem. It happens in the cloud as well because you want to think about being across zones, across regions, and you need to think about upgrading your kernels, which means you are going to be doing maintenance in the cloud. And of course, the cloud providers are going to be doing their own maintenance when they want to do maintenance, which means that you're going to have to deal with those failures. Or these days, if you get an email from Amazon, you might be able to do a little bit of preparation ahead of time, but you still have to be prepared for it. So the need for this new infrastructure really said, all right, let's move from this spreadsheet-oriented approach to the world where we'd kind of have these silos of machines, and we'd say, okay, these machines are for running this application, these other machines are for running this other application, these final machines are for running this last application, to a world where we can say, let's stop thinking about machines entirely, let's just think about the applications that we're trying to run, and let's put a layer of software in between the machines themselves and the applications that we're trying to run that can kind of be the arbiter between the applications and the software. And we can do lots of really interesting things there. One of the ones that's shown on this slide, which I'll mention later, is we can start to get some kind of portability across different infrastructures, whether it's on-prem versus the cloud. People could stop caring because they're just thinking about the resources that run their applications in, not the virtual machine or the physical machine that's been allocated to them. And then the other big one that I mentioned here is really increasing utilization. And so just a quick slide on that. The industry average for most machines is about 12 to 15%. And that's actually really generous. Most organizations that I talk to are like 3 to 8%. So utilization is incredibly low. And even in a virtual machine-based world, that's one of the really funny things is folks that have gone to the cloud, they're buying their 8-core, 8-gig machines from AWS, and they're using like a half a core and 1 gig, but they're still paying AWS for all those resources. And AWS is definitely stoked about that. Hope there's nobody Amazon fans in here. But the organizations are not so much. And just really simply by running more things on boxes, you can reduce the number of machines you want to run and really drive up the utilization. So this is just kind of an interesting perspective for me because when I show kind of the slides about increasing resource utilization and the slides about kind of putting this layer of indirection in between the stuff that's running, a lot of people say to me, hey, didn't we already do that? Wasn't that the virtual machine evolution? Wasn't that the virtual machine era? And so I just kind of want to capture what's really different here. And so I started with mainframe just because I think it's fun to tie it back to what happens at the end. We moved through this physical world where we actually managed a bunch of physical machines, and this was our sort of siloed, static, and monolithic and manual world. And then we eventually went from physical world to virtual world, where we started launching virtual machines. And first of all, what I thought was really interesting here was, for some organizations, all we did was just increase the pain, because we went from 4 things to manage to 9 things to manage. So it's just even more stuff that we actually had to manage. But for some folks, it was exactly what they wanted, because I don't know about all of you, but a lot of the operators that I've worked with in the past, they don't like it when cowboys show up on their boxes and do things like open up firewall ports or install random things. And so one of the biggest things that the virtual machine evolution gave operators was the ability to say, you no longer get to screw with my physical boxes. I'm going to give you a virtual box, and this will be your own little sandbox and playpen, and you can do whatever you want. But the problem for developers is that nothing changed. Right? The interface for developers was still a machine. Before, they were having to work with their operators to actually deploy on physical machines. Now they still had to try and work with somebody to deploy on virtual machines. And this, to me, is really why DevOps erupted, is because developers were now like given this machine that they had to deploy something with, and they had to figure out the best way to actually operate it. And so they started to do a bit of both. And really, the world we want to get to is say machines shouldn't be the abstraction. They shouldn't be the thing that's actually given to people, developers, to be running applications. Developers should just say, this is the application I want to run, and I need some resources to actually run the application. And in that way, we're kind of calling this more of a unified state, where you don't think about all the individual machines. You just think about the resources for running everything, for running your stateless microservices, your 12-factor apps, your stateful distributed systems, your analytics. And so the reason why I like to put mainframe in here is because if you squint, it kind of looks like a mainframe again. It's something with a bunch of resources that you want to run your applications that has some constraints. And in that way, we really think of all these machines being kind of just pooled together, acting as one really big data center computer. And that's your interface to how your developers should be running applications in the future, is this data center computer. And really, you start to get some principles that come out of thinking about these resources as just one big data center computer. And one is, really treat machines as cattle, not pets. Treat the base operating system really small and run these containerized applications, and don't have pets, don't have snowflakes in the data center where you really care about that machine or how that machine is operating or how that machine is configured. And automate with software, not humans. And I'm going to spend a bunch of the rest of the presentation really talking about what I mean by this when I say to automate with software, not humans. But getting back to some of the other things I talked about earlier in my presentation, it's letting software schedule software, letting software handle failures, letting software improve utilization, letting software manage maintenance, letting software do as much as possible, and keeping humans out of the picture as much as possible. And so, if you have a data center computer, then a data center computer needs an operating system. In the same way that the desktop had an operating system, the server has an operating system, my phone has an operating system, the watch has an operating system. If you're going to think about pulling all these resources together and giving this kind of interface to developers, then it needs something like an operating system as well. So that's actually what we're building at Mesasphere, and trust me, this presentation is not going to be a pitch for the product at Mesasphere. But it's really based off of the work that I originally started at Berkeley, and then we took to Twitter, which is Apache Mesos. And we really call that a distributed systems kernel, and I'll get into a bit why we call it a kernel in a little bit. But its main focus is to really abstract resources. So going back to that tenet that I said, don't think about the machines, just think about resources that you want to match applications to. So that's its main focus, is really to abstract resources. And then what we had to do at places like Twitter with Mesos is build a bunch of things around Mesos. And that stuff is what we've built around Mesos as well at Mesasphere and with some other partners in the industry. And that stuff all together is really what we call the data center operating system. So it's specific things to do with container orchestration, providing things around security governance, multi-tenancy, providing some monitoring operations things, providing a user interface, a GUI, a CLI, providing a package manager. There's a bunch of other things that we end up building around Mesos. And the main reason why we actually founded Mesasphere, the company, is because people that were adopting Mesos at organizations, companies like Apple and Netflix and a couple of other organizations that we were working with, they were having to build up these components themselves. And we didn't want to stick all this stuff in Mesos in the same way that you don't want to stick all this stuff into the Linux kernel. You want to have a place for this stuff to be able to live, and so you need kind of a home for that, and that home is really DCOS. And again, as I mentioned earlier, one of the big benefits of this is providing something like an operating system gives you the ability to now be portable to a much farther degree than previously across clouds and also on-prem. And I kind of already mentioned this slide, but really the way we see this is in the same way that there's the Linux kernel has operating system distributions like Debian, Red Hat, Ubuntu. The DCOS is kind of meant to act as that distribution that incorporates the bits that you really need to run your containers, your big data, your microservices, whatever it is in production, where Mesos really acts as the kernel. And architecturally, this is really the way we think about it. Like, we really think about keeping the kernel, the work that we actually put into Mesos, the code we put into Mesos, we try to make it extremely rigorous, whereas we'll put some stuff, for example, in user space that might be a bit more experimental, and then eventually we might push it down into Mesos. So we really do architecturally think about the way we build this very much like the way an operating system is built. It's a bit more of a microkernel style operating system, though, than kind of the monolithic kernels that things like Linux look like today. Okay, so from here I'm going to kind of dive into what is Apache Mesos then, and kind of explain a bit more of the tenets of Mesos so you can understand that part of it. And then from there I'm going to kind of transition into what are some of the things that you run on top, and sort of why Mesos makes it really valuable for doing that. So what is Mesos? So Mesos is really a general purpose cluster manager, which to me the most important thing, what that means is that it's not just focused on batch computation. And the reason I say that is because cluster management is by no means a new topic. It is by no means something that at Berkeley with Mesos we invented cluster management. Far from it, right? Cluster management is a very old field. There's been a lot of cluster managers that have existed for a long time in academia and in research labs in particular. Folks that were basically building applications using MPI, they effectively were using cluster managers or grid managers for quite some time. In industry, though, there was very different software that we were trying to run, and to me there's a reason why cluster management didn't come out of industry as much as it came out of academia. In academia, again, we're running things like MPI, which we run at a pretty big scale. And in industry, we're running things like web servers and web services. And when C10K, which was the idea of how many connections I could have on my web server, was a really popular thing in, I don't know, early 2000s, late 90s, it was because you only were running one web server, right? So you wanted to figure out the most number of connections you could actually get on that one web server, whereas MPI, it was inherently distributed. You're running it on tens, hundreds of machines. So at academia, they were already on hundreds of machines, and in industry, you're at 10, maybe one machine. You were running a web server, and you had one web server that you were serving tens of thousands of connections with concurrently. And so in academia, basically cluster management became a thing. PBS, Torque, SunGrid Engine, cluster managers existed. Industry, not so much. SSHing into the box and installing the software ourselves. When you have 10 machines, you don't even need a spreadsheet. You can probably just remember what's installed on each of the machines, because the machine's host names are like MySQL1, MySQL2. And eventually that transitioned to using things like Puppet and Chef, Capistrano and Ansible. But nowadays, that scale's really converged. And academia has gone to thousands of machines, and industry has really gone to thousands of machines as well. And so you need something like a cluster manager. But all the cluster managers of the past, they were really focused on batch computation, because the kinds of applications that were being run in the labs and being run in academia was really kind of batch-oriented. And so what we really did with Mesos was we said, let's build a new cluster manager that's not just focused on batch computation, that can also run service-oriented architecture kinds of applications, that can run things like analytics that are not necessarily batch-oriented. Maybe they're streaming-oriented. That can run things like databases, because why not provide the value of a cluster manager for something like a database as well? Okay, so at a high level, Mesos is a cluster manager with master agent architecture, pretty standard, looks like most cluster managers out there. But the biggest difference between Mesos and really what we did to sort of make it not just focus on batch computation was we introduced this notion of two-level scheduling, or a two-level model, where what we actually said was, let's build a system where, and so this is the part that is, I guess, a bit academic-y, maybe, but I thought it would be sort of, as an architecture conference, it would be interesting to incorporate this part to see sort of the underpinnings of where the technology come from, not just something that's being used in the industry, but actually how this came from some interesting ideas in academia. And so the model here is really two-level scheduling in Mesos. Where we have these things that in Mesos we actually call schedulers, but you can think of them as coordinators of different types of distributed systems that are trying to be run that communicate directly with the Mesos masters for actually running their applications. And I'm going to talk a bit more in detail about that. But really this idea of doing this two-level model really challenged the status quo of cluster managers at the time, of all the batch computation cluster managers. Because their model was something that looked a bit more like this. Oops, I guess the slide got a little specification show. So their model looks something like this. You'd have an application, or more likely you'd have a human that would submit a specification, declared a specification for what they'd want to run to the cluster manager. And then after they did that, and it would include as much specific information as possible to assist the cluster manager in scheduling and execution of that thing. And then after they did that, they would wait. And it was really interesting to chat with a bunch of organizations that were using things like trying to run some MPI jobs in certain grid environments, where they would say, yeah, we'd submit our job, and then we'd see that it would get queued up, and we'd be like, I wonder why it got queued up. Maybe if I run it with 10 less instances, it'll get run right away. So they'll pull their job out of the queue, and they'll resubmit it with 10 less things, and then it would get run right away, and they'd be like, oh, sweet, my thing ran. Now the job's going to run faster. But there was no kind of communication back and forth between the cluster manager and how it was thinking about doing its scheduling and the actual application and what was acceptable means for actually running the application. So anyway, you'd kind of wait, and then eventually you'd get your result. And so when you think about this, the problems with the specifications, with the specification-based model, with not this two-level model, was that in many cases it was really hard to specify certain desires or constraints, which led to, as I mentioned, humans actually sort of gaming the system completely out of band. And then the other one, which was much more relevant to us at Berkeley in 2009, was that it was really hard to update the specifications dynamically as tasks execute and finish and fail. And that was because the kinds of distributed systems that we were especially interested in running on cluster managers were things like Hadoop, which it's not really batch-oriented when you think about it. I mean, it's batch in the sense that you do a bunch of map and then you do a bunch of reduces, but it's very dynamic in when each of the pieces are finishing. Some maps will be bigger than other maps. The number of maps you need are dramatically different than the number of reduces that you might need. And so I'll talk about this a little bit later, but if you wanted to really drive up resource efficiency using a cluster manager, you'd need to be able to update your specification in real time. And again, I'm going to talk about that in just a second. But there's this bigger picture here, which is that the cluster manager really has inadequate knowledge of the distributed systems execution needs or semantics to make optimal decisions. And the distributed systems execution needs semantics can't easily or efficiently be expressed to the cluster manager. And this actually is just like a computer science thing that we've had for a very long time. It applies just as much to operating systems as it does to the cluster manager. And the analogy that I like to give here a lot is deciding which pages to evict in memory. The kernel just does LRU, right? It's like LRU is the best algorithm it has because it has inadequate knowledge of the application's needs or semantics to make the most optimal decisions. So it picked LRU, right? And meanwhile, the application doesn't have a great way to easily or efficiently express to the operating system that you picked LRU, but the next page you're going to take is actually the next page I'm going to read because my algorithm happens to be reading that thing. Wouldn't it be much better if instead the operating system could say to the application, hey, I need to evict some memory. Please tell me which pages to evict. So this is like not a new concept either, this whole idea of specifications being a tough thing. So back to the MapReduce specification and why is MapReduce so inherently hard to capture in this one-level cluster manager way? Well, again, MapReduce is really it's a couple of stages. It's not really map reduce, it's map, then there's a shuffle stage, then there's a reduce stage. And if there's kind of two different ways you can think about writing a map reduce specification. There's a fine-grained way, which is to say, I want to be able to specify to the cluster manager exactly the amount of resources I need at every step of the way. To be able to say, like, right now, I need 1,000 maps. 35 seconds from now, when 200 of the maps have died, I need 750 maps because so many have failed and some have died and whatever it is, right? In a minute from now, after all the maps have finished, I only need 7 reduces because in a lot of map reduce cases, you have far less reduces than maps. Or there's kind of the coarse-grained way, and this is, by the way that Hadoop was pretty much run on most cluster managers, which is just to say, well, I know that I need about 1,000 maps, and I've got about 5 reduces, so I guess I'll ask for 500 slots from the cluster manager, and I'll multiplex my 1,000 on that 500, and then when I run just my 5 reduces, I'll waste 495 slots, because maybe that's like going to get me the most optimal performance in terms of what I could actually share with the cluster manager. So this is just kind of the spectrum, and fine-grained is almost impossible to really articulate to cluster managers today, and coarse-grained gives you really bad utilization. So in the Mesos model, we said, why not instead have the distributed system directly register with the Mesos master in order to run its computations? So have something like Hadoop directly register with Mesos and be able to say, at every point in time when it needs resources, hey, these are the resources that I need right now. So not, here's run this right now. It's just these are the resources I actually need right now. And then, the Mesos question that we really had to ask ourselves is, what could we do if like a request came in for resources and we couldn't actually satisfy that request? And there's really only kind of 2 options. One is we could wait to satisfy the request, until we actually had sufficient resources to satisfy it with. And the other one is that we could just say, well, we couldn't satisfy your exact request, but here are the best resources we could give you to try and run your job right now. And that kind of gets back to that example I was giving earlier where the human would submit the job to the grid engine, and then they'd be like, oh, maybe if I removed 10 instances of this thing, I'd still be able to run it. So rather than having them guess, what if we could just say, hey, here's the best we can do in terms of resources right now? So that's what we actually did in Mesos, and that's really what the essence of this 2-level model. And so in the Mesos model, we have these things that we actually call resource offers, which you can think of them as allocations. They're available resources for you to use at this point in time. And then these coordinators, these schedulers, these Hadoops or Sparks or HDFSs or whatever it is, they get these resource allocations, and then they can decide, mini resource allocations, and then they can decide what's the best way to run their applications after that. And then they kind of launch tasks, and then those tasks all get scheduled and run. And this is really an invariant of multi-level scheduling. And I think sorry, one more thing. So the first level in Mesos is really, the first level of scheduling is really about making the allocations to these things that are running on top. And the second level is about the distributed systems actually deciding what things they want to run with those resources. And so Mesos really acts as this level of indirection, as I kind of mentioned earlier in the presentation, where Mesos ends up being responsible for the allocation and reallocation of resources, and in this way we can really efficiently share resources across a bunch of different things and drive up the efficiency. But what has been more interesting, where we started the project, and what's been much more interesting as the project has evolved and as we've used this at a bunch of organizations, is that this level of indirection doesn't really just provide support for allocation and reallocation of resources, but a whole bunch of other things. It's not just resource allocation, so I'm just kind of reading some stuff from the side here, or resource deallocation. It ends up being things around multi-tenancy for resources, so things like resource reservations, resource isolation, resource monitoring, doing failure detection, actually distributing your tasks so you can run them, having life cycles for how the tasks actually run, and a whole bunch of other stuff that we can really start to provide at this layer. And getting back to that analogy that I was sort of mentioning before, the operating system analogy, this is why we really think of it as a data center kernel, because it starts to provide a bunch of these primitives that distributed systems can much more easily take advantage of for building those distributed systems and also for operating those distributed systems. And the biggest difference really in terms of an operating system architecture between it and traditional operating systems is this two-level bidirectional thing lets us, when we need to, introduce certain communication that would allow us to not run into kind of the LRU predicament. So when we want to introduce a new primitive to do something, we can kind of introduce that, and we have this bidirectional communication between the systems that are running on top and Mesos itself. And I've just got this little thing at the bottom, which is don't reinvent the wheel, which is just, it's interesting because, you know, distributed systems are actually really hard to build, right? And pretty much everybody ends up rebuilding a lot of the same components into their distributed systems because there isn't something like a distributed systems kernel or a great distributed systems library that everyone starts with, right? So they all end up rebuilding their own means of failure detection. And there's a bunch of great research papers about which are the best ones, but the fact that we have thousands of implementations out there is probably not an ideal situation. You know, on top of them just being really, really hard to build, they're extremely hard to operate, deploy, maintain, update. And so I kind of wanted to spend a couple of slides talking about, you know, as we've seen the evolution of how you run some of these distributed systems on top of Mesos and in the DCOS, how like this has become a really you know, one of the most valuable parts of our two-level model. And when I say, you know, distributed systems are hard to operate, deploy, maintain, and update, I literally mean that there's like a whole, you know, book industry of how you actually run distributed systems. And this is, to me, this is what it looks like when people are operating distributed systems today. It's like, okay, so I want to run this distributed system. So I download it, okay. Then I deploy it. Now, what's the best way to deploy it in my data center? Well, maybe I go buy the book, and I read the book, and I read about what's the best way to actually deploy this thing. You know, because I'm curious about what's the best high availability setup, what's the best arrangement for performance, who knows what. You know, then once I get it deployed, I want to monitor it. So I want to know, like, what's the best way to monitor it? What are the endpoints I care about? What are the metrics that are really important? You know, what are the metrics that the guy programming the distributed system know are like, wow, this is a really important metric. Somebody should monitor this one, because if this metric goes down, like, the system's in a bad place. Like, you know, how am I going to get that information as the operator? I'm going to have to go read a book or something, right? And so now I've got this thing deployed, I've got it monitored, and now I want to maintain it. So a failure occurs. So first I got to debug, like, why did this thing happen? Why did this get in a state where it wasn't doing what it's doing? So I debug, I go back to the book maybe, keep reading the book, or I go ask the internet, or I go to the IRC channel, and it's 2 a.m., so I'm like really frustrated, and I realize the way to fix it is to just run this one command. I run that one command, everything's good. Okay? 3 days later, it's 2 a.m. again, and I get woke up, and I'm like, you know what? I'm smart. I'm not going to get bothered by this ever again. I'm going to write a script which is going to recognize when this metric says this thing, and it means I need to run this one command to actually update this thing. So I'm going to write this script. So I'm going to go write that script. Okay. So I fix the problem. You know, I update my run books to tell other people what they need to do if it's 2 a.m. at night. I write these scripts. Or worse, what we see in a lot of organizations is I build entire ancillary systems to operate the distributed systems. And those tend to be these piecemeal things that get actually put together. But you show up at a lot of organizations and you find out about, like, oh, yeah, we run Cassandra and we've got a control plane for Cassandra. We had to build our own control plane to actually operate Cassandra, because to do it in any kind of logical way is nuts unless I just have a whole bunch of scripts. And of course, this gets even crazier if I want to upgrade or redeploy. And so, you know, we just really have this perspective with Mesos, which really ties into this two-level model that I was talking about, which is these distributed systems should be able to leverage all these primitives that we can put in Mesos so that they can really operate themselves. They can deploy, monitor, update, upgrade, everything. And I think the crux is that to enable operating systems to actually do this, to enable them to kind of have a control plane, if you will, for operations, they really need an interface that enable them to communicate with the underlying infrastructure. And they really need those primitives. And that's really what the operating system or the kernel interface really provides. And that, you know, that's kind of the crux of what Mesos is really providing these systems more and more. And again, getting back to the bigger picture, humans have inadequate knowledge of distributed systems, need semantics to make optimal decisions, even after reading the book. The operator still does not have the most optimal things. The programmer who probably built the system knows far more than the person who's ever operating in it. But it can't easily, what the system needs can't easily or efficiently be expressed to humans and/or underlying infrastructure unless there was actually that interface. And so this is, when you think about Linux, it's kind of a different perspective of the way you can think about this. But applications on Linux, they really operate themselves, right? When they need more CPU, they get threads or they fork processes. Right now, it's not like a one-to-one thing. We don't actually really have a way in operating systems to say, give me another CPU. I mean, we can say, like, give me another thread, and then pin its affinity to a different core, so I make sure I'm actually getting more CPU power. But it's the closest thing that we can really get to it. But when they need other operations, like when they want to read or write to a file, when there's other primitives, when there's other things that they need to do, they get that all from the operating system. They basically ask the Linux kernel for that. Could you imagine running an application on an operating system the way that we kind of run distributed systems? When Chrome wanted like another CPU, you get a little pop-up that's like, hey, Chrome wants more resources. Like, why don't you pick which CPU is the best CPU to give to Chrome to get some more resources? But that's not what we do, right? It just says the operating system, I need more resources, and it just does what it needs to do. So why can't we have something like that in the data center as well? So distributed systems can really operate themselves. When they need more CPU, they can ask Mesos for more CPU. When they need operations to be performed, like getting a persistent volume, moving persistent volumes, any of these kinds of primitives, they can ask Mesos. And so, to me, there's this future world for distributed systems with these control planes, effectively, where the software is really going to manage itself, using Mesos and something like the DCOS API. And there's a kind of a crux of these that we're specifically focused on at Mesasphere, which is in the big data space, and that's what I'm going to show a demo on in just a second. Things like Kafka and Cassandra and Spark, and you don't need the books. And so the joke I like is that when people say, Mesasphere, who are you trying to disrupt? We say we're disrupting O'Reilly, because you're not going to need to publish any more books, and people will just run software. So, these control planes, these distributed systems, as part of the DCOS, we have a package manager, effectively. We call it the universe. Everything is very space-themed at Mesasphere. Mesasphere is a layer in the atmosphere. It's the layer that's just above the clouds. That was just lucky, because the project Mesos was called Mesos a lot longer, and Meso means middle, and we used to think of Meso as being this middle layer, and like Mesopotamia, the Middle Earth. So we're just lucky that we happen to have some. Anyway, so we have this package manager, and there's a bunch of things in the DCOS that you can run that basically have these control planes. Now, one of the things I want to be really clear about is not all of the things that are in our universe have control planes, are these two-level scheduler entities. There's a lot of stuff. In fact, I'd say 90% of what people actually run on the DCOS is just these stateless microservices. They just have a bunch of these microservices they need to get run and they need to get deployed. They're just the easy ones to schedule. They're the easy ones to deal with when it comes to failures. There's the easy ones to deal with when it comes to maintenance. The really hard ones are things like the databases and the analytics, the message queues. And so those are the ones that are a bit more interesting. And so I actually wanted to show a demo of what I mean to kind of put all this stuff together. And so I'll do that now, and then I'll take a couple questions. So what I'm going to do is I'm going to show the DCOS, and I'm going to show, so one thing I forgot to mention. So Apache Mesos is an open source project. The DCOS is also an open source project. You can go to dcos.io, as I mentioned at the bottom. Anyone can contribute to it. So everything I'm going to be showing is you could go do this yourself afterwards. So I'm going to launch a couple different applications. And this is kind of getting back to this idea of in future world, modern applications are a collection of microservices, storage, and analytics. That's just the way pretty much any organization, what an organization is having to do. So I'm launch this thing that we call Marathon LB, which is a load balancer. So Marathon is in fact Marathon is one of our it's a container orchestrator. It's our container scheduler. It's one of these coordinators that specifically deals with nothing else except just launching these stateless microservices. So then I'm going to launch 2 apps. I don't know why I typed app plus Marathon. I'm going to launch 2 apps. One app is going to be something which is reading and showing tweets, showing your timeline, basically your Twitter timeline. And the other app is going to be generating tweets. And I'm going to use Cassandra as the key value store. And then I'm also going to, the tweets, Kafka is also going to be pulling the tweets that are being written into Cassandra and putting them in queues so that we can run some Spark streaming computations directly off the Kafka queues and then actually run some Spark SQL to ask questions of what's actually happening. Okay, so let's see if this just magically shows up. It does not, so we'll stop this for a sec. Maybe. Okay. That's not ideal. Okay, just a sec. Let me. Well, I can't see my the entire page. I think it's just because of the way it's plugged in. I'm just going to unplug for just a sec and then re-plug in because this worked just a second ago. That looks better. What's that?
Not so much on this side.
That looks better.
There we go.
Okay, now you can see the whole thing. Okay, so so I've got a terminal over here on the right, just because, as I mentioned, as part of this, the DCOS, we have both a GUI and a CLI. So the CLI, so I've already installed the DCOS on AWS, and you can follow the instructions at DCOS.io to do the same. And then once that happens, you can come here and you can install the CLI, and we just have some instructions for how you actually install the CLI. So, we've just kind of got a pretty basic dashboard here. I'm going to kind of be bouncing back and forth really and looking at the services. This is a 9-node cluster, so nothing really big. The universe, as I mentioned, which is those packages that you can use. So there's a bunch of community ones, and then there's also a bunch of ones which are we have selected. Selected just means that we actually introduced something of an RFC-like procedure for some packages. So for example, if you are something like a Cassandra, we've got things that say like you must deal with a failure. You should provide the ability to do upgrades. Like you may do. So we just kind of got a doc like that, and the things that we haven't selected are sort of matching that criteria, whereas the things we have here are not necessarily matching that criteria. So your mileage may vary. And so what I'm going to do here is, so I've already downloaded the CLI. Can you guys see that? Should I make it a little bigger? Is that visible? OK. So I'm actually going to install a handful of things. So as I mentioned, one of the things I was going to install was Marathon LB. So Marathon LB is just, it's a microservice. It's a microservice that's helping me do some load balancing from external traffic to internal traffic. And so this is just a package that's in the universe. I'm going to go ahead and say yes to get this installed. And so as a microservice, it's basically being launched by Marathon. So as I mentioned, Marathon was sort of our thing for running container orchestrations, and I ran this yesterday for a handful of folks, so ignore all the killed things, but you can see what we'll soon be running. So you see Marathon LB, which is now up and running. Another way to think about Marathon is Marathon's kind of our init system for the data center operating system, in the same way that like initd or systemd, the first process that then you run all the other processes from. That's another way to think about Marathon. OK, so I've launched Marathon LB, and now again, I know I need Cassandra for my storage. So I'm going to go ahead and I'm going to install Cassandra. And so what's happening here is what's being installed is we basically have this bundle, which is both the control plane, or the Mesos terminology, framework scheduler, as well as just open source Cassandra. So we haven't modified Cassandra. We haven't tweaked Cassandra in any way. We've just taken open source Cassandra plus this control plane for actually running and operating Cassandra. It's a little bit different than some of the other frameworks that we launch, where it's all bundled up as one thing. In Spark's case, the control plane is effectively part of Spark. But in certain cases, they're separate. In certain cases, they're together. So I've launched Cassandra. And then the other thing that's happened here is I've got a new subcommand, which is Cassandra. You see that here, installing CLI subcommand. So I can do things if I want from the command line to actually interface with that control plane. But there's also a web UI that's you can go to the Cassandra web UI or the control plane web UI, which currently you can't get to, unfortunately, from the open source version, but you will be able to soon. So this is coming up. Cassandra's actually coming up. So it's got one task so far. And there's a default way in which Cassandra comes up, where it just spins up two nodes. So it creates a ring of size 2. And that's configurable. When I package install Cassandra, I could have passed other configuration options. But I mean, what I think is pretty powerful here is, I guess I was wrong. It's 3. What I think is pretty powerful here is, this is all just happening, right? The control plane is all just managing this. It's installing this. It's figuring out what are the right resources in the data center for running this. It's getting its persistent volumes in the cluster. It's reserving reservations for the jobs after it runs. So when you think about a stateful service in one of these dynamic environments, when you go and deploy something like Cassandra and it starts to run on a particular box, it should probably run there as long as possible because it's using its persistent volumes. I, as an operator, didn't have to ahead of time go and say, hey, these are the boxes I'm going to use to run Cassandra. I just exposed what boxes were available, and the Cassandra control plane said, these are the boxes which satisfy what I need to actually run Cassandra. I'm going to get a reservation for those resources now. So if anything were to happen, if I were to die, if the machine were to reboot, whatever it is, I can reschedule my jobs on that box so I can keep running. So there's a bunch of things that are actually happening under the covers that humans would have manually been doing in the past that now is just all being taken care of via software. And so, OK, so that's Cassandra. So we get that up and running. So I also, and so there's this subcommand. So we can look at what the subcommand. So it actually tells us what's happening. And I think one of the what's been run. And one of the other things to mention that's really interesting is one of the components of the DCOS is a DNS server that we run. We run a DNS server. And every single container that Mesos schedules, it gives it a DNS name that's based on the task identifier information. And so you can basically address everything that's happening directly via DNS. In certain circumstances, DNS is insufficient. And so we've got a bunch of other networking stuff that I'm not going to talk about today. But in many circumstances, DNS is just fine. So, OK, so what else? We need Kafka. So I'm going to go ahead and package install Kafka, just cheat a little bit, pull it up from my previous run. So I'm going to go ahead and install Kafka. And Kafka, again, very similar to Cassandra, needs some persistent volumes, needs to get those things allocated to it, get them reserved. We'll see Kafka start to pop up here in just a second. One of the things I think is interesting is you see Cassandra as a full-blown service. If we jump actually into Marathon's own web UI, Marathon's got its own more focused web UI, you'll see that we've got Cassandra and Kafka running here. These are those control planes. So Cassandra and Kafka are actually communicating back to Mesos to run their other things, but just to run the control plane part itself, we run that through Marathon. And that's why I was saying, in the same way that kind of when you run your first application with like systemd, and then when it wants more resources or it wants to fork exec its own processes, it goes directly back to the Linux kernel. That's kind of the model here. We launch the control plane for Kafka, and then it goes back to Mesos to launch its other processes. And so you don't see Cassandra's other processes here, Kafka's other processes here, because the process tree is really just this. But the process tree specifically of Cassandra itself is that it has these other things that it's launched as well. And so now Kafka, it came up and it launched its 3 brokers. So I guess 3 is the default for both of them. 3 brokers, three nodes for Cassandra and Kafka. OK, so I've brought those guys up, which is great. And again, I can look at Kafka and I can see the broker names and DNS so that I can actually communicate with it in other circumstances. OK, so now I'm going to actually run some microservices. So I'll refresh this page just so you can see that there's no application that's currently running here. And the microservice I'm going to run is a little app, which is going to be reading from Cassandra. It's going to be both reading and writing from Cassandra. And when you run an app, a container app, there is a specification for the container app. Which I think is very interesting, because I had a presentation earlier where I was talking about, like, no, specifications are bad, we should know specifications. But in certain circumstances, specifications are sufficient. They're exactly what you need. And in this case, this little app that I'm running isn't trying to do anything fancier in the data center. It just kind of wants to run and be left alone. And so we have a little specification for running it. And so I'm going to look at that now. So this can be YAML or JSON. I'm showing the JSON version. So this is a little microservice app. It's called Tweeter. It's got 3 instances. It's coming from the Mesasphere Tweeter Docker image. So it's a Docker image. It's a container based on a Docker image using NAT. It's got health checks, which I think are really cool that we have this built in. So it's a different kind of fault tolerance. For all the applications that are running Mesos health checks every single task that's running if you give it the health check information. And so you can know whether or not the task, not just if the machine fails, but if the task itself has decided that it's unhealthy, it can get rescheduled. So you can specify these. So this is an HTTP health check. And port 0 seems actually very confusing, but it's the port that's going to get assigned here. So in the same way that if you just want any ephemeral port from Linux, you just say 0, and an ephemeral port gets assigned. The same thing's happening here. And then it's got a couple of labels that we throw in there that are specifically so that the Marathon LB application that I mentioned before can properly route the public traffic. And that's what's happening here. But I've launched Marathon LB, but it says service unavailable because there's no Tweeter service currently running to route the traffic to. So that's that. And I did I slightly changed this, but I'll just show you what the diff is. The only thing that I did was I added in the public load balancer for the app. So you could run this in any one of your clusters. You just have to update, if you're on AWS, to use the public load balancer. OK, so now I'm going to go ahead and I'm going to run this. Oops. So this is saying, to the Marathon subcommands, there's a bunch of things I can do in the Marathon subcommand. So these are all the things I can do. So it's very much like Git like this, or subcommands, and you can do lots of things. I'm going to add the tweeter.json application. So go ahead and bring that up, and we'll see in a sec here that it's going to get deployed. So this is basically just speaking the API to the DCOS and to Marathon to actually get this deployed. So there we go. It's up. 3 instances are up relatively quickly, and it's running. So now what I'm going to do is I'm going to go to the app and refresh it. And so there we go. So now we've got our microservice up and running. And I think this is the part of this new world that is so powerful, is giving people the ability to kind of get things like microservices like this up and running so quickly. In the early days at Twitter, the executives were interested in it for cost-saving reasons. but the reasons why the executives ultimately were most interested in it is just because of the agility that it gave the team for on day one being able to launch a microservice and get it scheduled somewhere in the cluster. So you could go look at it and play with it and actually do something with it. The big turning point at Twitter when there was kind of this mandate that every single new application would get deployed this way was when we did a hack week, and it was the most impressive hack week that the execs had ever seen, because all of a sudden all these hack projects were usable and people were playing with them, and they're like, how did you do that? Like, how is that running in the data center? What happened? So just kind of a side note that I think is interesting. So I can tweet here. And oops, and basically that's being written to Cassandra, and then this app is also reading from Cassandra. So it's showing the tweets. But now I'm going to launch another app, and another microservice, and just to kind of show you that there's other ways to launch it, I'll launch it through here, the create application, and I'm going to call this one tweet. It's actually going to be the thing that's tweeting, and I'll give it 2 CPUs and 512 megs of RAM. It doesn't need any disk. A single instance is fine, and I have a cheat sheet here because I always forget that line. And so this is the command, and so it's also going to be a Docker container, and it's coming from Mesasphere Tweeter, and the command is kind of basically it's going to tweet Shakespeare. So it's going to take Shakespeare, and if you were the first lieutenant or something, and you say a line, you're just going to tweet as handle first lieutenant, and then it's going to be your line. So that's going to be all the tweets. And again, it's just communicating with Marathon LB that I can use the DNS names for, and it's a Docker container. Notice there's like ports and service discovery, environment variables, and labels, and health checks, and a whole bunch of other things I can do that I'm not going to do. But this should look very similar to the JSON or the YAML that I showed a second. Question?
I was looking for the tweets you just did, and I missed. What are we doing here? Are you creating a new application based on the Docker image?
Yeah, so I'm launching a different microservice, and this new microservice is going to be tweeting. It's going to act as like a bunch of people tweeting, basically. So because I can't type it in, I can type in all those tweets. And so let's make sure I spelled that correctly, Mesasphere Tweeter. And then, we'll go ahead and I'll create that application. And so that's now getting deployed. Well, it already got deployed quickly. So once I run this demo enough times, the deployments are super fast, especially for the Docker containers, because we've already downloaded the Docker containers. If I ran it the first time, the deployments would be a little bit slower because you'd see us, we're actually pulling down the Docker container and running it. And you notice there's no health here because I didn't add a health check. I specifically didn't add a health check. So I'm going to go back to the DCOS API now, and you'll see that in Marathon, well, first you'll see if I go to Tweeter and I refresh, now there's a bunch of tweets. So I was never a big Shakespeare person, but this is Shakespeare. And we can go back and we can actually grab that tweet app that I just mentioned. You can see the files in its container, and we can look at the log viewer, and you'll actually see for every single tweet that it sends, it writes it out to standard out. And so you'll see in a second that this will refresh, and it'll ask me if I want to scroll down, because it just keeps, so go to bottom. So here's all the new tweets that it just keeps sending out. And meanwhile, I can come back here and refresh, and we see lots of new tweets. OK, so microservices, big data, Cassandra, pumping into Kafka. What's the next step? So the next step is let's go ahead and let's do some analytics. And to do that, I'm going to install another app called Zeppelin. Has anyone heard of Zeppelin? Zeppelin. So Zeppelin, you can think of Zeppelin as basically an IDE for Spark. If you've used IPython notebooks, it's basically a notebook for Spark. Completely open source, not our project. It bundles Spark. We took it and made it, because it bundles Spark, and Spark already has, Spark already has a control plane directly for Mesos. It just becomes a distributed system that works right out of the box for us. So we're going to go ahead and install Zeppelin. And again, it's just coming from that package repository. So here it goes. It's going to get installed. This one, you notice, didn't come from the selected packages. So We're very clear to say that this is experimental. There may be bugs, incomplete features, or incorrect documentation, which is true. Zeppelin sometimes just does not work. The app just does not work for me. So this is where the demo gods are hopefully going to be great. But so this is actually it. I doubt that it's loaded yet. Let me just refresh. Yeah, so it's not loaded just yet. It's still being deployed here. So we'll wait for that to happen. We can kind of watch. And again, this is basically the control plane is what's being deployed. And here's where it's being staged. So here you see it bundles Spark. We can kind of look at what's happening. It's fetching the files it needs to fetch. Hasn't really written a standard out yet, but soon it should be up. It's still deploying, fetching those files. And so then once Zeppelin is up, what I'll do then is I'll actually run a couple Spark jobs. And really the power of what this is trying to show is that the Spark jobs are just elastically being scheduled right on the cluster, just like everything else, getting the resources that they need. In fact, I can run multiple instances of Zeppelin at the same time. I can run Spark completely separately. I can run multiple instances of Spark, which is usually something that you want to do in a bunch of these environments. And it's deploying. And oh, awesome, we had a failure. Woohoo! Which is great, but it got rescheduled faster than I could get to it, which is also good.
Was that built into the demo?
No, it wasn't. Sometimes, depending on time, I probably won't do it today, just depending on time, but I'll go and I'll actually kill machines, see them get rescheduled. I'll kill a machine for a really long time, and you'll see the control plane for Kafka kick in and decide after a certain timeout that it's going to re-replicate its data to other brokers. Or sorry, not Kafka. Cassandra will re-replicate its data to other nodes. And then the other demo that I sometimes show is actually doing an upgrade of Kafka from one version to another version, where again the control plane is managing, upgrading one instance, making sure everything's healthy, upgrading the next instance, making sure everything's healthy, and then rolling back if anything fails. So Zeppelin's now up, which looks good. So I should be able to come to this page and refresh it, and then sure enough, there's Zeppelin. So here we go. So now what I'm going to do is I'm going to import a note that I already had in Zeppelin, and basically it's the notepad that I already have, so that we can so that you can kind of just see. I'll just walk through this kind of quickly. So the Tweeter Analytics notepad, and so here's the notepad. You kind of saw it a second ago, but now it's all up and connected to our Zeppelin cluster. And so the way the notepad works is you can just write Scala code using Spark, and then you can basically just run the commands. So this is not necessarily what you'd run in production. This is what a developer would use to figure out the algorithms they might want to run across the data that actually exists. And so this is great. Every single developer can have their own Zeppelin running, using whatever resources are available in the cluster. I haven't talked about a whole bunch of other components like reservations, quota, other things that are making sure that developers only get as many resources as they should get, but all things that you could imagine are vital in things like operating systems. But yeah, and so it just I want to run Zeppelin. I want to try it out. I can just launch this as a developer and run my jobs. So that was a really quick one. That one finished. This one's the one that takes a little bit longer. So this is where I'm actually now going to be reading from Kafka, and I'm going to be I'm basically going to be looking at the counts of who spoke the most in the Shakespeare. So it's really just counting the number of jobs. So this one took 16 seconds. Now, what's cool about this is, as I mentioned earlier, Zeppelin now shows up as a first-class service here because it launched Spark. And Spark acts as, again, a distributed system that has its own tasks. And so if I jump into Spark, you'll actually see that there's a bunch of tasks here that are running. These are all the Spark workers that just got allocated and launched, so I could actually run my Spark job. And just to make it so, so this is all Spark. So if you know Spark, the coarse-grained executor backend, the memory store, There's probably RDD somewhere mentioned here, RDD 26. So this is Spark. Spark is just now running in a cluster for Zeppelin. So now I can go back here. Again, this is just going to keep updating because my tweets are going to keep coming in. And now I can run some SQL where I specifically am, again, based on running the Spark job, over that time, sorry, it's a Spark streaming job. So over that window of time, I can now get the counts that I want and see who talked the most. And so it was all right. Cleopatra's up there, which I'm happy about. Okay, so that's kind of run everything, and that was the demo that I really wanted to show. Just hey, you can launch all these things, you can run all these things using the resources and the primitives from Mesos and the DCOS. And so I'll just wrap it up now, and happy to take lots of questions. I wanted to leave about 10 minutes for questions. So I guess I just had 2 more real quick slides. So one was recently some organization we've been working a bunch with is okay is Autodesk, which is an organization we've been working with, and this did not render very well. But the big thing I wanted to just say is this sort of reduction in AWS instances is very real for a lot of organizations because you really can pack more resources on a bunch of machines, and that's pretty cool. Anyway, DCOS is an open source community. You can check it out. You can contribute to it. You can suggest ways of improving certain aspects of the software architecture. You can do whatever you want. And again, as I mentioned, you can check it out at dcos.io. And I'll stop here and take any questions.
I have a question. How do you set up your hardware or like AWS instances before you start running this magic DCOS?
DCOS. Yeah, so for AWS, we actually do have an installer for installing everything from the operating system, the kernel, the host operating system, and DCOS. You can check it out on dcos.io, but basically it's a combination of CloudFormation templates, which you can tweak if you want, and you can add more nodes for each CloudFormation template. So it's an AWS stack, which is a couple of different CloudFormation templates that we use to actually bring up all the pieces. On-prem, we also have an installer on-prem that's far more rudimentary, that is using a combination of pretty much SSH keys and IPs for installing DCOS itself. Once the DCOS is up and running, adding a new node is trivial. You just install the bits on it, connect it to the masters, and it's up and running part of the cluster.
What is the minimal amount of resources you need?
Great question. So again, as I mentioned, it has a master agent architecture. If you want to run HA for the masters, you need 3 masters at least. And then we've got some folks that have three masters and 2 agents because they still they just want to run a couple things. They want to get some fault tolerance across those 2 things. We have some people that run actually 1 master and 2 agents as well. When you go to run some of these other things, as I showed Cassandra, they take real resources. So you have to be prepared for that. If there's no resources, then the jobs can't get scheduled, and you can monitor metrics that show you like, hey, these jobs are still pending. There's not enough resources. Probably what we'll do in the DCOS in the not too distant future is hopefully somebody from the community will add a feature where it'll just recognize that case on AWS and add another AWS instance. The CloudFormation templates are set up in auto-scaling groups, so it's really easy to add more instances.
Hi. So I'm going to try and phrase this question a little bit. So I'm a little bit interested about the Cassandra and how the recovery works, especially with the persistence, right? So one of the things that came up when we were talking earlier this week about containerization was this idea of how do you capture intent and then make sure that your configuration is kind of in line with the intent, right? So I know with Cassandra, you were mentioning, if there's a failure, it'll detect it, things like that. But of course, in your code, if you don't have your quorum set up correctly, your read-write, consistency in the right ways, you could, I don't know, I imagine you could get into a state where you can't do anything for some period of time, right? I don't know. I guess my question is like, what was there a spec for Cassandra? Like, did you just skip that step, or like, how do you reconcile these things that have to be consistent, consistent across the system here?
Yeah. So basically, what ends up happening for most of these control planes, like the Cassandra control plane, is it usually has some kind of a working set, and that working set. I'm using the term working set to like literally refer to like its memory effectively that it needs to operate the underlying project, which in this case is Cassandra. And all of our control planes pretty much today store that in a key value store. The DCOS comes with one, which is Zookeeper. There's also a way to run etcd as a key value store on top of the DCOS. But they store in the key value store their intents. And that way, if they fail, because again, I showed you that the Cassandra scheduler control plane was running via Marathon. If it happened to fail, Marathon will just rerun it someplace else, and it'll get back its state. It'll reconcile the world, and it'll try and continue to make progress from where it's at. Most of the system is exactly based on this idea of recording your intents, sending off your requests, reconciling in any cases of failures. Because like who knows whether or not your request made it. Perhaps your request made it, and the response that your request has been satisfied made it, but you were down, you were partitioned, whatever it is. So there's a reconciliation step that always happens, looking at the intents and then the actual state of the world, what tasks are running, what tasks are not running. And so there's no real specification for Cassandra for that control plane piece. That specification for that is really simple. Sorry, there is one, but it's just very simple. It's like run an instance of this forever. And if it fails, it just comes up somewhere else, gets its state, and then keeps going.
Okay, so there's a difference between the control plane, and then I still have to manage the Cassandra cluster itself in whatever way, and that's not controlled by Marathon.
It's controlled by the control plane.
It's controlled by the control plane, which is controlled by Marathon.
Yeah, I mean the Marathon launched the control plane for you, keeps it up and running no matter what. And then in the same way that you launch an application via initd, and then it fork execs more of its own processes for happening, the control plane fork execs more of its own processes and then manages those.
Two questions. One, does this work on Azure? And the other question is more, how did you performance test your scheduling component?
Yeah, so the first question is like I paid him in the audience or something. Yeah, not only does it work on Azure, but Microsoft, they built the Azure Container Service, and it uses the DCOS. It's based on the DCOS. So if you want to kick the tires with containers on Azure, you can use ACS, which uses this directly, which was different than what Amazon did. They built their container service completely from scratch, ECS. And Google built their container service, GKE. And then what was the second question? The second question was performance test.
Because I suppose that becomes like as more tasks run.
Yeah.
Right? They're going to be going to this like center point to figure out where to go and run.
Yeah. Well, so part of the benefit of the two-level model is that we actually can in parallel do more scheduling. So for example, when you're running multiple MapReduces, you don't have to do all the scheduling for all the possible MapReduce tasks at the first level scheduler. You do the allocation of resources at the first level scheduler, which I mentioned was called offers, and then each of the individual MapReduces or Sparks or whatever it is decides based on those available resources what it wants to schedule. So you're actually doing some scheduling in parallel. Now, some of you might be thinking like, wow, that sounds complicated. Can that actually work? How does that work? And then I've got a whole presentation which is all about the intricacies of that and some of the primitives we've had to introduce to make that work well and to make that scale. But kind of my off the cuff answer is that Mesos runs on clusters that are upwards of 20, 30,000 machines just for allocations, and so we've done a lot of work on doing scalability testing? This is not a good answer. Let me try and change it. We do actually do a bunch of scale testing for our allocators where we'll run hundreds of these control planes up top and on simulated 50,000 node clusters where we'll take like a 500 node AWS cluster and run a handful of agents on it so that we don't actually have that many machines, but in terms of what the master sees, it thinks that it has that many agents that it's actually communicating with. And that's what makes it expensive, is having to go through all those machines and figure out where it should allocate the resources. So we do that still, but we also just have, we find bugs in the wild all the time that we have to fix in terms of performance. And so that's the other thing that we do, is we actually just fix the bugs or performance regression issues when we see them in practice.
Hey, it seems like there's a lot of kind of processes that don't necessarily fall directly into the model of the service here needs this amount of resources and it'll inform you when it needs more or less.
Yeah.
But rather, for example, if you're running a big MapReduce job, you might say, if there's 20,000 CPUs available, I can use all of that.
Yep.
But on the other hand, if there's a front-end load balancer that goes down and needs to be rescheduled,
Yep.
that's a much higher priority and
Yep.
it should preempt it.
Yep.
Is that something that is kind of handled through this? Or?
Yeah, so it's a great question, and it's a big thing. It's a big part of what we cared about in the resource allocation and management of resources in Mesos itself. So I kind of mentioned earlier we have concepts of reservations and quota, and so priorities is one model. It's not a direct model that we went down. And the reason is we didn't directly go down it is because it's harder to reason about priorities as organizations grow and scale. Like what you just said is like if Marathon LB or if the load balancer goes down, you want to make sure there's other resources out there. Like who knows, maybe somebody else launched a job that had slightly higher priority and like they didn't realize that was higher priority and then we scheduled the wrong thing. So with reservations and quota, it's much more concrete. It's like I want to make sure, like the risk I'm willing to take is that the load balancer, I'm willing to take the risk that I only need to run the load balancer on one machine, but I want to have enough quota to make sure I can always run it on 3. And I'm willing to take the risk that worst case scenario, we lose so many resources that 3 was not enough, that I should have actually, or we're running so many jobs that 3 is not enough, I should have actually asked for something else. But it's just much more concrete. You can you can do capacity planning with your teams and you can say, what do you want to, what kind of failure scenarios do you want to deal with? What's the exact capacity you need, worst case, best case, and then you can express that versus priorities. So that's how we actually capture it today. Reservations, quotas, and then for kind of everything, I should say we do have a notion of priorities. They're called weights. And so for everything else, the resources are just weighted. And so for different jobs that are running, we'll give you like for every 1 CPU that this person gets, you get 3 CPUs. And that's another way of kind of capturing some priorities with weights. But honestly, at the end of the day, when you're working with an organization, you really care about that concreteness of like I want to make sure that even in a weighted situation, you might lose so many resources. You're like, well, I got to get my 3 machines worth of resources.
Okay, we have time for one last question.
Anybody else? Okay, I have a question about cost.
Yep.
Like, can you define like a cost parameter to this system, like do not exceed X amount of dollars or do not exceed X amount of resources or things like that?
Not yet, but it sounds like a fantastic contribution.
Thank you. We'll try.
Okay.
Okay.
No, I just like a little bit on that. We collect all the metrics of how many resources you're actually using. We have all that information. We'd like to funnel even more of that information back into the allocator. We did a bunch of that work last year with Intel. We actually introduced the concept of oversubscription. So you can find resources that are not being used, and you can oversubscribe stuff, and then we use that information of what's actually being consumed. We actually had like a Hack Week project where we took all that information and we printed it out in a spreadsheet so that we could show organizations you can like kind of get like a charge back. But there's a lot more information we could do with that, and we're not really doing much of it yet.
Okay, let's all thank Ben for the great presentation.